Last time we started covering how to map coding functions to math functions. We started looking at some of the examples for this. So we looked at a quadratic versus a linear example here, and we found that there was an inflection point in the graph. And we also learned that we care much more about how these functions scale rather than what happens at small values of n. Because it doesn't really matter how inefficient it is, at small values of n, any computer will be able to handle it regardless of how inefficient it is. So all we care about is how it scales, because your implementations are also going to be scaling moving forward. So we care about the scalability of your implementation. How does it map as we start making this a word I want to use for this? English frequently leaves me. Enterprise code, we'll go with that. Not quite what I intended, but. So we talked about scales and making sure that we're looking at an appropriate scale. So if your x-axis is so small that it makes it look like there's one over the other, that one is better than the other, there can be some hints in there that tell us that maybe we should zoom out and look at the actual asymptotic behavior. We talked about different orders of functions. We had a table here where we could actually go look at some of these orders and their associated names. We'll be playing around a little bit more with those today, and also applying this to some coding examples where we're going to be analyzing some code and trying to figure out what order is this code in based on the code itself. So I think we stopped on this slide in the middle of it, so we're going to start here. We looked at this, we asked, between these two running times, an squared minus b log n and cn plus d, we asked, does it matter what the values of these coefficients are, a, b, c, and d? And the answer was no, it does not matter, even if c and d are massively huge, like in the order of billions or trillions, and the order of b is really large. So we're subtracting something from something that is quadratic. As this scales, the quadratic will still take longer than the linear as we get to a reasonably large enough n. We also asked what the orders are. We found that one was quadratic and one was linear. The question I don't think we quite got to was, since these algorithms accomplish the same task, which one should we decide to use? It would vary, sure, if we have reason to believe that this doesn't scale to the same level, but assuming that we have a reasonably scaled program. Which one should we use? One or two? Two, absolutely. Two will scale much better than one does. Let's find another example. Here's algorithm one that has running time in an cubed plus bn squared plus cn plus d. And another is n times n plus 1 all over 2. So let's start with the question, how do we figure out what the order of algorithm 2 is? Multiply first? Yeah. Basic algebra. We're going to distribute the n. We would get n squared plus n over 2, which is the equivalent of n squared over 2 plus n over 2. What order is that in? It's in the quadratic order. Has anyone seen or heard of this expression before, n times n plus 1 over 2? Have we seen that before and know where it comes from? It is a very, very commonly found expression in computer science. If anyone's seen it before, where does it come from? Yeah.
I don't know.
Yeah. So this comes up very, 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 very frequently in computer science as the actual representation of the sequence 1 plus 2 plus 3 plus up to some value of n. If you have this sequence, can you imagine an algorithm or something that you've written before where the analysis of that would lead you to say, we do 1 operation, and then we do 2 operations, and then we do 3 operations, and then we do 4 operations. Yeah?
Like maybe looping through a list, and then every time you loop through it, you add another item to it that you.
Yeah. So if we're doing something like we want to parse an entire list and then add something to the end and go back to the beginning and parse it again and continue to do this process, this is very common if you're doing something like sorting the list. You want to figure out where something goes in the list, and we have a partially sorted list, and we have some rest of the list that is not sorted. We may want to figure out where one of the elements goes in the list. We'll have to compare it until we find where it goes. We'll actually talk about this later. But the reason that this sums to n times n plus 1 over 2 is you can imagine that for some instantiated value of n, let's copy this and reverse it. So we would have n plus n minus 1 plus etc. I think this is easier to see if we actually instantiate a value of n. So let's just say that we want to sum to 10. I can replace the n's now with actual values. We have 10 plus 9 plus 8 plus. If we sum each column, what do we get? 11. We get 11 plus 11 plus 11 plus. How many 11s do we have? 10 of them. So if n is 10, we have 10 11s. And then what did I do to the original to get this? If this is the original list, what did I do in order to get this expression? I duplicated it. So the sum of this is going to be the sum of this. So we just divide this by 2. We see that 10 was our n. 11 is the sum of what we did for each column. And then we divide that by 2. So in general, whatever the value of n happens to be, this will just become n times n plus 1 over 2. So we will see this over and over and over and over again throughout many different classes in many different contexts. So it's useful to remember that this exists, and it will help us to be able to, if you can just map this concept to the order quadratic, because that's what we did here. We determined that it's in the quadratic order. That's great. You see something that works like this algorithmically, you will know it is quadratic without having to go through any of this associated logic. But it is absolutely worth seeing once. Questions on anything that I did or how I derived n times n plus 1 over 2? All right, so which algorithm should we use? 1 or 2? 2 once again. Yes, quadratic is less than cubic on that table. So algorithm 2 will finish before algorithm 1 as we scale n, regardless of what the value of A, B, C, and D are. Two more algorithms. 1 is an cubed, and 2 is n factorial. Which one is going to scale better? Now, factorial wasn't in that list of running times. So we will often find that we end up with some function that may not be precisely in one of the running times that's in some kind of table. So we will need to use any understanding of math that we have to try to manipulate it and place it and say it is better than this or it is worse than this. So what can we do? Yeah, that sounds like a really good idea. So we know that n factorial is n times n minus 1 times n minus 2 times can we compare this expansion to any function that we saw in the running times table, in the order table? What is it map closest to? Yeah, exponential. So we know that 2 to the n, so I'm going to write this as n factorial equals. So if it had 2 to the n, what would that look like? Multiplied by something. So instead of this n, we would have 2. Instead of this n minus 1, we would have 2. Instead of this n minus 2, we would have 2. Is one of these obviously greater than the other as we scale the value of n? N factorial is definitely bigger than that, right? N is going to be bigger than 2. Let me draw this as like a greater than. N minus 1 is going to be greater than 2. The only time we're going to have something equal and then less than is right here. But every other element is not only greater than 2, it's probably significantly greater than 2. So we could use algebra to just show that as n scales, that n factorial is worse than exponential. Do we remember just how poorly exponential scaled from yesterday's lecture? We made the exponent 10 times larger, and we found that the ratio between something that was quadratic and something that was exponential just exploded. So now we have reason to believe, we know that factorial is an even worse scaling than exponential. It is just about the worst you can find. You could probably find something like exponential exponential. You can start making towers of towers, and those grow stupidly fast. Now, let's transition and think, can you think of an algorithm that runs in factorial time? Recursion is usually significantly better than that. A good guess, though. You have to start thinking about really inefficient ways to do things. My go-to for an algorithm that's in factorial time is called BOGO sort. Has anyone heard of BOGO sort before? Yeah. I've renamed it to bozo sort because nobody should ever implement it. It is just about the worst way you can think of to sort a list. What would be the worst way to sort a list that would finish that you can think of? BOGO sort basically says, take the list, randomly permeate the list. Check if it's in order. If not, do it again. If not, do it again. So let's say we had a list of 5 elements. How many times would you think you have to randomly sort the list, randomly permeate the list in order to get the first element in place once, on average? If we have 5 elements, we're gonna have a 1 in 5 chance of hitting it. The other 4 times it's gonna be something that doesn't belong in the first place. So just to get the first element in order, we have to sort the list n times. To get both the first element in place and the second element in place, how many times do we need to sort the list? N minus 1 times. So we have to both get the first element in order and get the second element in order. And get the third element in order, and get the fourth element in order, so we can start to build the factorial expression as we think about this in terms of how many elements are in order starting at the beginning. And we need to get all of them in order. It's a very large and in order to sort the entire list. So this is factorial. If you haven't seen just how fast factorial explodes with growth, it's pretty amazing. And to think that if we tried to do this, implementing BOGO sort on a list of 20 elements, it would not finish before you died. 20 elements, that is all. Kind of scary. So throughout the quarter, we're actually going to discuss many ways to sort lists, because there are lots of ways to do it and lots of ways to be aware of, because they also help you to understand some algorithmic concepts that will be useful going into your algorithms class. So this is just kind of a hint of, we're gonna leave BOGO sort and never talk about it again. It's just that bad. So the next thing we might care to do is, how do we actually get these mathematical functions out of our code? You write a program and you have code in front of you. How do we actually get a mathematical order? So far, in everything that we've talked about, I just said, here's the mathematical order. I've not at all talked about how this happens. So let's start by thinking about, how can we look at code and convert that code, analyze it, and turn it into a mathematical expression that represents how long it will take to run. So if we have a program and we wanted to figure this out, we could do things like run it for input size 1, run it for input size 2, run it for input size 3, do that 10,000 times, plot it on a graph, and do some kind of curve of best fit to that. That sounds really tedious. I have no interest in writing that program because there are much easier ways to do it, but it is something that you could do to be able to map something that we've talked about to this idea. Rather than just running the code, it would be better if we could just analyze the code. So programs are made up of operations. These operations can be things like an addition, a subtraction, an operator like plus plus, which actually is an addition. You'll find that most things that happen in code break down into some basic building blocks. We can do a comparison, something like, is A equal to B? Each of these take about the same amount of time. So if we could count the number of operations that happen throughout the entirety of the code and turn that, rather than just some constant because we don't know, we can phrase this in terms of the input size. So there will be some variable like n, the input size. Just like we've seen a n cubed, etc. This n is going to show up as we figure out how many times is this run based on the input size. So we're going to count the number of operations, holding n constant, or rather keeping n in the expression as we analyze the code. We could use this as an approximation of the running time. It will map reasonably to the number of milliseconds that the program takes to run, but it's not going to be perfect. It's going to be close enough to identify an order that will tell us where in that table this code lies. So we must ask, for every operation that we write, how many times is it executed? This may be a constant number of times if it only happens once. If the very first line inside of main is int a equals 4, that's only run once. It's not inside of a conditional that may be run or may not be run. It's not inside of a loop that may be run multiple times. It's not inside of a function that may be called multiple times. It just happens once. So you may end up with something that is a constant. You may end up with something that relies on some kind of variable, like n. If you loop through something the number of input times and have a single line of execution inside of that loop, that line gets executed n times, once for each pass through the loop. So programming constructs can make this a bit more complicated. And we'll see this with some examples. So an example from this will be the size method that we wrote for our linked list class. Does anyone recall what was inside of that linked list size? What code was inside of this function? Yeah. So we have a field for size. So we just said, return that field. There's a method that gives us access. It's just the world's simplest getter. Returns the value of the field. So think about how many operations are executed. if we have a linked list of size 1, or a linked list of size 2, or a linked list of an arbitrary size n. How much work is it to call that size method? How many operations will be executed? Just one? Regardless of the size of the list, right? The field has a value and we just access the value of that field. We're not doing anything inside of a loop. We're not doing anything complicated at all. Regardless of the size of the list, this always has the same complexity. It doesn't ever get more than a single call, a single read to the field and return it. So regardless of the size of the list, it only requires a single operation, which tells us that the order of this is constant. It's theta of 1. It does not matter what the size of the list is. Does it make sense as to why that is constant, or how we link this concept of constant to the running time of this particular method?
Is it only one because you're just doing one like action, you're describing one thing?
Yeah, even if it was exactly 7 things, and it was always exactly 7 things, it would be in this order that we call constant, theta of 1. There's no theta of 7, or theta of 12, or theta of -3. They all represent the idea that there's a constant number of calls, a constant number of operations that are done, regardless of the size of the input. Great clarification. Now I'm going to throw a wrench into the plan. We don't have the size field anymore. We need to now figure out how many elements are in the list by iterating over the list. So we need some kind of logic that is going to return the size of the list rather than just reading a field that we've kept track of as we've added to or removed from the list. So let's start with writing. You can use a computer for this, you can use paper for this, whatever you prefer. Write a little bit of code that would accomplish returning the size if we did not have a size. How are we doing? People want more time? Raise your hand if you'd like more time. All right, so it should look something like this. And note that this code uses the E generic rather than the T generic, but it does not actually matter which one we use. So we're going to have some counting variable. This code calls it tally. We're going to set a node to be, they call it front, we called it head. We'll set a node to be the head. And we can now iterate through the list as long as the current node is not null, then the update is just getting the next node. As we do this, every single time, we just add 1 to the size of our counting variable. Once the loop terminates, we return it. So now, rather than using exactly the code that you wrote, since it should be basically the same as this is spaced in such a way that will hopefully help us to be able to do this associated logic. I will zoom back in just a second. Let's ask how many operations are executed in this code when the linked list has a single node, or 2 nodes, or 3 nodes. See if you can come up with a function. So first, write it out as a table. With 1 node, how many operations are we doing? With 2 nodes, how many operations are we doing? And go line by line in this code and determine how many times is this line executed. And then draw that out as a table. What is the second expression with curly braces? That's just the internals of the loop. The way that this is set up, this is a for loop that the definition of it ends here. It's covering 3 lines rather than the usual 1 line that we've seen in the past, or that you probably implemented yourself. The reason this is done is because each of these lines may be executed some different number of times. So I wanted to put them on different lines to make sure that you could write expressions for them separately, rather than just having 1 line that has a different number of times that it's run based on which section of it it is.
Kind of unrelated, what's the meaning of this element?
That's the generic. So we don't know what kind of node this is. It could be an integer, it could be a double, it could be a person object, it could be anything.
Okay.
Whatever it happens to be instantiated with. It's the same as our T from the code that we wrote in the first week. Feel free to talk to your neighbors too. This does not necessarily have to be an individual task. Introduce yourself, get to know the people around you. Your table should look something like this, and the actual work is figuring out what goes in the number of operations side of the table. So when size is 1, how many times are each one of these things done? First line, how many times is it done? Once. Done once. How about this setting the node to front? How many times is that done? Once. We don't do that every pass through the loop. We just do it once as the loop initialization. How many times do we check if node is not null? So we check it the first time. And is the node null the first time? No. We then do something, we loop back around, is the node null the second time?
Yeah.
Yes, so we do this twice. How about node equals node dot get next? How many times do we do that? So this isn't done until the very next pass through the loop. So we first do this, then we loop around, and as we loop around, we do this once. Then we check this, and it's false, and we fall out. So it's actually once. How about the tally plus plus? Once, we do that once. And how many times do we return the tally? Once. So sum that up for me. How many operations do we have for size 1? How about for size 2? How many times do we set tally to 0? Once. How many times do we set the node to the front? Once. How many times do we check if node is not null? 3 times. This is now changed between a list of size 1 and a list of size 2. It's the first thing that's done that. Node equals node dot get next. Twice. Tally plus plus, how many times? Twice. How many times do we return tally? Once. How many operations do we have? 10. Do we have enough information now to turn each one of these into an expression based on the size of the list? How many times are we going to do the first thing if the size of the list is n? The very first thing, set a tally to 1, always going to be 1, so I'll set this as 1, 2, and n. So this is going to always be once. How many times do we set the node to the front? Once. How many times do we check if node is not null? So if n is 1 and it was 2, 2 and it's 3, then this is going to be n plus 1 times. How many times do we do node dot get next? N times. Tally plus plus, n times. Return tally once. So we sum all of these up, what do we get? Three n plus 4. What would we expect if the size was 3? 13. So now we can start applying this to these constant values by doing a substitution of n for 3. 3 times 3 is 9 plus 4 is 13. And we start to see a pattern emerge. We could plot this and it would make sense. We would have something that is 3n plus 4, and here are the values of 3n plus 4 for the domain 1 through 4. But all of this work combined helps you to be able to actually put this into practice. What's the order of 3n plus 4? It's in theta of n. Great. Any questions about any of the work we did to arrive at this associated order at this exact function that details exactly how this code works? No questions? That all makes sense? You feel like you could do something like this on homework or on an exam?
Yeah.
Let's find some harder problems for you to work on. So this is pretty close to as easy as it gets. We write code frequently that is much more complicated than this, and we also want to be able to analyze code that is more complicated than this. So we did all of this work. We did exactly this. So we can see in the comments here exactly what we derived, but I wanted to make sure that I went through the logic so that you saw how this was derived. We determined that our function was linear. Great. Here's the next piece of code. We are going to look at a deck class. And it's going to be doing something a little bit more complicated. So work with your neighbor or some neighbors around you and see if you can come up with the associated logic and determine what order this deck constructor is in. Rather than just using n as a single variable, we should use suits and ranks, because some things will depend on the number of suits and some things will depend on the number of ranks. So rather than using n, use s to represent suits and r to represent ranks. So a rank is like a 2, a 3, a 4, a jack, a queen, an ace. And a suit is the clubs, spades, diamonds, or hearts.
How do you know if spades is considered less than club?
Yeah, you have to know the underlying code. Assume that it iterates over all of the suits. So if you had done an enum, for instance, that set spades to 0, something in the middle, clubs to 3, then you could do something like this that iterates through the enum. So yeah, that for loop is going to do something the suits number of times, however many suits there happens to be. We'll just make an assumption that spades is the first one and clubs is the last one. How are we doing? Who wants more time? Couple people? Take a little bit, let's take 38 more seconds, see if you can polish out as much of this as you can take an educated guess. I just hear that second. All right, let's see if we can figure this out. So just like before, let's go line by line, but I'm not gonna build the table this time because I feel like we probably have the tools now to just be able to jump straight to the generic variable version of this. So we're gonna use R where it has to deal with the number of ranks, S where it has to deal with the number of suits. And let's try to figure out how many times this is run. Cards equals new card 52. What did we decide? It's done once. Is it any more complicated than a simple operation? No, it does not matter how large this array happens to be, you're allocating space for it. You're not going through it and doing something to it. Although that's actually technically not true in Java. Does anyone know why that is?
Because it doesn't automatically, I don't know.
There are default values for everything. So if you make an array of integers, it will go through and set everything to 0 at the beginning. If you have objects, it'll make sure every one of those objects is null. If you have an array of booleans, it will go through and set everything to false. So this actually happens. There's the assignment and then 52 settings. So this is really 53 times, but generically for an arbitrary programming language, we're going to call this as done once. How about size equals 0? Once, regardless of the size, great. How about this suit being set to card.spades? We're going to do it exactly once. This is set once, and then by the time if we loop back around this loop, we never do the setting again. We will do this check multiple times. So this happens once. How about suit is less than or equal to card.clubs? So we're gonna have to check it for the very first time. I think you're right. So we'll have an S plus 1 times. How many times do we bump up suit?
Once.
We're gonna have to bump it up from spades to, let's say, diamonds is next. We're gonna have to bump it up from diamonds to hearts. We're gonna have to bump it up from hearts to clubs. And then we're gonna have to bump it up from clubs to something else where we realize that this is false. So there should be 4 times, since there are 4 suits. This is done S times. How about the rank equals card.ace? This would happen, yes, actually, it is the suits number of times, because this loop is going to be started each time we go through this outer loop. So the initialization that we do here as card.ace is going to happen once to make the ace of spades, once to make the ace of diamonds, once to make the ace of hearts, and once to make the ace of clubs. So this will happen S times. How many times do we check if rank is less than or equal to card.king? So this happened S time, S times. So this will also happen. We're gonna set this once for each time through the outer loop. But then we also are gonna do it for each rank and then once at the end so that it's false. So this is S times R plus 1. Whenever you hear something that says for each or additionally, something of the sort, think multiplication. For each suit, we need to iterate through the ranks. So how many times are we going to be doing a check? For each suit rank pair. We get the plus 1 for the extra time that we are going through, and this becomes false, and we verify that it's false. The rank plus plus,
S times R.
S times R. All right, now we're inside of this for loop. We're gonna do this for each time we're in this time, each time we're in this. How many times are we making a card? S times R. And then how many times we're bumping up size plus equals 1, size plus plus? S times R. So now we want to sum this entire column. What is the associated expression with this? So let's distribute. We have S times R plus S. That'll make this slightly easier to see. So how many S times R do we have? 4 S times R? How many just S's do we have? 1, 2, 3, 4. How many ones do we have? 4. 1, 2, 3, and we'll count that one as separate. So the entirety of what we have determined here is 4SR plus 4S plus 4. Now the real question, is this linear or quadratic? Yes, so if suits is something that can vary, if you see something like the very top that says, num suits or something, a static num suits equals 4, that can't change. Static final int. So that way we could replace this S with 4. But since this could vary, this code could represent some deck mechanic that has more than 4 suits. So because of it, we prefer to keep it written like this. And that way, we will know that if S is something that is final, then we can instantiate that as such. So we are very out of time. I apologize for going over by a couple of minutes. But I wanted to make sure we finish this off. We can come back and talk about it again tomorrow. I will be in my office for the next hour if anyone has any assignment related questions. See you tomorrow.
We can do that.
Are you heading to the office right now? Yeah. That's good. Last done? Yeah. Are you free for class? Both the TA and I might be slightly busy. Oh, okay.
Yes.
Absolutely.
See, buddy, this one day.
I know, I